Welcome to the next series in my webinar on modern Java by example. Today, we're going to talk about the Reactor framework, which is a newer, more modern version of what's found in RxJava. And the reason why these two frameworks look so similar is they're both fundamentally based on Java 9 reactive streams and the interfaces that it defines. So what I'm going to do today is show you how to implement the folders application that we've been covering over the past few times, except this time using the Reactor framework, and it'll also give us a chance to compare and contrast Reactor with other mechanisms that we've covered, like RxJava and parallel streams and sequential streams and completable futures. So without any further ado, let's go ahead and share my screen and we can get started. So come down here, share the screen. And the first thing we're going to do, I'm just going to show you where you can find the source code. So the source code for this example is in my live lessons folder, and it's under the folders folder. And in here, it's under Reactor. And so this has got all the source code, and it's also got the files that we're going to read as part of this program. So just again, for completeness, some of you have already seen this before, but for those of you who are coming to this new, I have a very large test folder that contains thousands of subfolders and documents. And this is kind of what it looks like if you were to go ahead and look at all the contents. It basically is the contents of all the source code I provided in an open source form over the years written in Java. So it's just there for, give us something large to analyze. So the first thing that this particular app is going to do is going to read all the contents in this folder, which is a recursively structured set of subfolders and documents, up into an in-memory data structure called a folder. And then we're going to go ahead and process it, do various things, count the number of lines, search for search words, count the number of entries, and so on and so forth. And this will give us a chance to compare and contrast how the Reactor framework handles this processing versus the earlier things that we've seen that do the same capability. In particular, we're going to talk about comparing and contrasting with RxJava because they're very similar. Okay, so let's now go ahead and turn it over to my IDE. And if we take a look here in the source folder here, you can see that we've got an entry point program called main. And this is structured somewhat similarly to the version we saw before that's based on RxJava. They look very similar at a high level. And that's no accident because they both implement the same core set of interfaces and have a lot of same operations and other characteristics in common. But you'll see, I think, that RxJava is a little bit more older and a little bit more idiosyncratic, whereas the Reactor framework is more modern, uses Java 8 and beyond features a lot more effectively than RxJava did. Okay, so you come in here, you can see that we're going to run a bunch of tests. We're going to run everything sequentially using this one test method with the flag set to false. We're also going to go ahead and run all the tests concurrently with the flag set to true. That should look very familiar to you if you've seen my earlier videos. And then we've got a new test called run test parallel. And this uses the Reactor framework's parallel flux mechanism. And it's kind of cool. And it also performs very well, as you'll see here in a second. I'm not going to spend a lot of time going through this because you've probably seen it before, but I just want to recap it briefly to refresh your memory. Or if you haven't seen it before, you might want to go back and watch the earlier videos just to get a sense of what the driver application's like. So we have the run tests method that takes a Boolean that says whether to run things concurrently or sequentially. We go ahead and run a bunch of tests using this clever timer framework that I put together that allows us to run the tests, and then it records the time so we can compare them in an apples-to-apples way. And what we do here is we go ahead and create a folder, and we actually get back a mono. So for those of you familiar with RxJava, you're probably familiar with the concept of a single. And a single is a bit like a completable future. It is really meant to be a future to one computation. In the Reactor framework, this is called a mono for various reasons. We get a mono back to the dirent, that's the root of the recursive folder. And then we're going to use that mono for other things as we process and do the other tests. So once we've got our mono, then we can go ahead and search for folders, looking for search words. We can count the number of entries, and we can count the number of lines. And we'll look at all those methods and see how they're implemented with the Reactor framework. One thing I do want to note, though, because we had talked about this the other day, I decided to have some fun, and I kind of upgraded and enhanced my create folder method. So now it returns a mono, but unlike my previous example, which had used a hot single in RxJava, this time I'm just going to go ahead and use a cache. So by caching this, every time I go and read from that mono, it'll give back the same results without having to regenerate the results again. And that approach seems to be more consistent and more portable than using hot single. It also seemed more appropriate in a way than using hot single, which really has other meanings in other ways, or hot observable. All right, we'll take a look at this more in a second, but you can see already that the structure here is very similar to RxJava. Now let's just quickly look at the run test parallel method. This does more or less the same thing, except this time it's going to run all the tests using the parallel flux mechanism. And parallel flux is very similar to parallel flowables in RxJava. And in fact, it turns out that flux is actually a term that means flowing. So like you may say a project is in flux, or there's a flux of people, an influx, for example. So that's where the flux comes from in Project Reactor. And of course, there's also this concept of a flux reactor, which is an energy generating model. At any rate, that's a bit of a side note. So these methods are going to use the parallel flux frameworks to do all the operations. So we're going to create the folder in parallel. We're going to go ahead and search the folders in parallel. We're going to go ahead and count the lines in parallel. I didn't bother doing counting entries in parallel because it's ridiculously fast to begin with, and there was no point in doing a parallel version of it. And you'll see that as we go through this in just a second. Okay, so let's kind of dig down a little bit and take a look at the different implementations using these mechanisms. So let's go ahead and take a look at create folder. And create folder is going to use the from directory method, which is going to go ahead and take a path name or file and read the contents into a durant, and then it's going to end up returning a mono to that. So let's go ahead and take a look at what that looks like. So here is from directory using the Project Reactor mechanisms. So the first thing we're going to do is we're going to take our flux, which is kind of like an observable or like a flowable. In fact, a flux is really more like a flowable. Observable was a construct, a class that was from RxJava 1 before the Java Flow API and Reactive Streams API had come out in Java 9. So it's still around for legacy purposes, but it's kind of being subset or sunset for the newer mechanisms that are available. So let's go ahead now and take a look at what we do. So we're going to go ahead and read the list of files from the root file, and that's going to be used as an array, because of course list files comes back as an array. We're going to create a flux from the array. And that's kind of like from iterable, except it works on arrays, not on iterables. So a flux is like an observable or a flowable. It's basically a stream of entries. So we really have create a flux stream from a list of files. And then we're going to go ahead and use the reactor flat map idiom, which is basically the same thing as the RxJava flat map idiom, in order to be able to run the code either concurrently or sequentially. Now, one of the things I've observed after writing a lot of RxJava and Reactor code recently is that it tends to get very repetitive if you're not careful. And I hate unnecessary repetition. So I started building these little helper methods that simplify my code. And I think I really like the way it turns out because it's a lot cleaner once you understand what the helper methods do. So what I'm going to do here is I'm going to take each file that comes from my list of files, and I'm going to go ahead and call my Reactor utils just concurrent if helper method. And you can see that takes an entity, a file in this case, and a flag. So let's go look at just concurrent if. What just concurrent if does is it uses a flux just factory method to omit the element that was passed in, which you can see here is generic. So it's an element of type T. In our case, it's going to be a file. And it's going to go ahead and then call something called transform deferred. Transform deferred is basically the Reactor equivalent of compose from RxJava. And we're going to go ahead and transform defer this thing into a concurrent flux if helper method. And concurrent flux if is a little helper method I wrote that will either have this run on the common pool, or it'll have it run in the caller. So those are, again, little helper methods I wrote. So common pool Flux, as you can see, will basically subscribe the Flux on the common fork join pool. And of course, you could subscribe to other pools as well. I'm just using the common fork join pool here for consistency. And then the other one that we saw here, the calling Flux, that just basically turns into a no-op. So that says keep it on the current thread. Okay, so that's what concurrent Flux if does. It essentially returns to us a Flux that's either been subscribed onto the common fork join pool, or it's just going to be in the calling thread. You'll also notice something else interesting here with Project Reactor. Because it uses modern versions of Java, what it returns here is a function. And so unlike the previous RxJava code, which had this thing, I think it was called observable transformer or transformable observable or some convoluted ad hoc thing, this is using Java 8 functional interfaces, in this case function. So that's just a little cleaner. Okay, so let's back out here. So what this is going to do is it's going to either convert this Flux into being a concurrent Flux, or it'll keep it as a sequential Flux. And that's the starting point of all this. Then we go ahead and filter out the path to get rid of redundant infinite recursion loops with the root path. And then we go ahead and apply flat map to create entries given the path that we've got. So you can see here we've got a path, and the path, of course, is the path that's the file that we've got, and it's going to go ahead and create a new entry. And so if you take a look at create entry, you can see this is almost identical to the RxJava version, except it uses mono as opposed to single. And it takes a file entry, and then if the entry is a directory, it recursively creates the second subdirectory. And if it's a file, it goes ahead and makes it, gets a document from the path. And you can see that this also looks almost identical to the RxJava code. We just end up using mono instead of single. But mono and single are essentially the same thing, more or less. The main difference is that in RxJava, a single has one element, whereas a mono could either be 0 or 1. And that's because in RxJava, they have this thing called a maybe, which is either 0 or 1. And so a single is 1, a maybe is maybe 0 or 1. So that's, in some sense, a bit more like a mono. But they're very similar otherwise. So what we're doing here is we're basically creating a stream, a Flux stream of these entries, and that's all being done either sequentially or concurrently using the just concurrent if trick that I showed up here. You'll also notice that this code is a lot more stripped down, and there's less gobbledygook in it, for lack of a better term, than the RxJava code I showed before. You could apply the same techniques to RxJava too to also get them clean. Now this is kind of cool. So what we end up here when we're all done is we're able to use a collector. So this is one of the cool things about the Project Reactor mechanisms, because they're based around Java 8 abstractions and beyond. You can use all the things you're familiar with. So in this particular case, we're going to essentially take this Flux and we're going to collect all of its entries together. And to do this, we just use all the standard streams capabilities. So we say collector of. So collector of is just a factory method that comes out of garden variety streams. And we're able to make our own custom collector. So we're going to collect into a new folder that's rooted at root file. And then we're going to pass in the accumulator and the combiner. And these are just simple methods in this class. So nothing tricky here. Go look at add entry. You can see that add entry takes a dirent and either adds it to the subfolders list or the documents list, and then it increments the sizes correctly. So that's what add entry does. And then merge, as you can see, this would simply go ahead and merge one subfolder's contents into this subfolder's contents, and then update the various sizes and so on. So that's pretty cool. So one of the nice things about Project Reactor relative to RxJava is it uses modern Java features. So that's kind of cool. So this code will work either concurrently or it'll work sequentially. For kicks, let's now take a look at the from directory parallel version. This is the same idea, except it's going to use the mechanisms in Project Reactor that use so-called parallel fluxes. And again, it's going to look very, very similar to what we saw before. It just, we tweak a few things and it gets a little bit more concise because parallel fluxes are inherently more concise for parallel processing, as you might expect. So here we're going to use from array parallel. That's another little helper method I wrote. And you can see what from array parallel does is it uses the flux from array factory method to convert the array into a flux. So this actually converts the array into a flux. And then we go ahead and we convert that flux into a parallel flux, which is very much like converting a stream into a parallel stream. And then we go ahead and run this particular parallel flux on the common fork join pool. Again, you could run it other places. I just put it there. No big deal to parameterize that too if you felt like it. So now we end up with a parallel flux. We get rid of the root folder to avoid infinite recursion. And then we're simply going to do a flat map, and we're going to pass in create entry parallel, which is a method reference we're going to look at in a second. Keep in mind that all of the code from where we create the array in parallel down to the end of flat map, that is all now running in parallel on separate rails. So if we go here and look at create entry parallel, you can see all this does is it just takes the file entry and it either recursively starts another directory download in parallel, or it goes ahead and creates a document. Either one of those things can take place at this point. What we do when we're all done is we go ahead and we convert the parallel flux back into a sequential flux, which is just a flux. And to do that, you have to use the .sequential operator on parallel flux, which turns it back into a conventional sequential flux. And then we just use our collector. So again, this looks pretty much identical to what we see with regular Java 8 kinds of streams code. We take a flux of durents and we collect them together into a custom collector, which is going to be rooted at the root folder. So the code is very, very similar between the two. You can see the main difference is we don't have to do this secondary flat map here. We don't have to do this little flat map idiom here. All we have to do is just use the parallel flux mechanisms. And I think it's very clean. This code looks quite a bit like parallel streams with just a little bit more syntax to convert back and forth and so on. But with the proper set of wrappers, I think it's almost identical, which is pretty cool. Okay, so that was those are the methods that create the folders. Now let's go ahead and take a look at some of the other methods that run the tests. So some of these things are pretty straightforward. Let's go back to folder tests. So we showed how to create a folder. Let's now show how we count entries. So in this particular model, we're going to take a mono to the durant that's rooting the recursive hierarchy. And then at that point, we're going to go ahead and start doing some different processing. And I show 3 different ways of doing this processing here just for kicks. I haven't quite decided which one I like the best, but I'm playing around with it. So you can give me feedback on what you like. So the first approach, we just got to kind of go ahead and write it all in line. So we're going to take the mono, when the mono is done, when we're finished initializing the root folder, then the flat map method gets called. That's kind of the completion stage method, if you will, using completable futures terminology. And in this particular case, then we're going to go ahead and take the root folder, which we now have because it's finished being initialized. And then we're going to go ahead and use from iterable concurrent if. And this is a little helper method I wrote, which will go ahead and take the item, which in this case is an iterable, it's a durant, and then we're going to go ahead and turn that into a flux, and then we're going to transform deferred, which is the way that Project Reactor composes things together, and then that will go ahead and do a concurrent flux if. And we already looked at concurrent flux if. That either makes it concurrent and schedules it on the fork join pool, common fork join pool, or it just basically returns the same flux as a no-op, and it doesn't do any concurrent processing at all. And then all we do is we just go ahead and count the number of durants in the stream. So we get a bunch of durants, either concurrently or sequentially, and we count them all up. And if it all works, we call do on success, which is somewhat akin to the then apply method that you would find in completable futures. And that'll give us back the entry count. And then we go ahead and print the number of entries in the folder is the entry count. And the last thing we do here is we block. And I just happen to block here because I want my test to finish so I can time it properly. Obviously, you'll see some other examples later of other ways of handling this. So that's what we can do for count entries. Let's take a look at search folders. This shows a slightly different approach to writing this code. And keep in mind, for my aesthetic of programming, I hate to repeat myself, and I hate to have really long, fluent interface chains. I find those things are quite unreadable after a while. If it starts getting beyond sort of one page or one screen, I get lost. So I like to keep things in smaller chunks. So what you're going to see here is we're going to go ahead and take the root folder mono, and we're going to take the search word, and we're going to take whether we're searching concurrently or not. And then we're going to define ourselves a couple of one helper function. And this function we're going to call count matches. And this uses good old Java 8 mechanisms. It uses the functional interface. You can use the same trick, by the way, in RxJava. It is shown a little differently and syntactically, but it's the same trick. So what we do here is we go ahead and take a dirent. So for each directory, for each entry we're going to search, or each directory, or each document, we're going to go ahead and search it either concurrently or sequentially using our just concurrent if factory method. We're going to filter out any documents by using a little helper method that just checks to see if it's a document. And then the last thing we're going to do is we're going to count the number of occurrences. And this occurrence count method looks very, very much like the version that we had for RxJava. Let's just take a quick look at it. You can see what it does is it takes a document and a search word, and it splits the document up into words using split as Flux, just like split as observable in RxJava. We only keep the words that match the method reference here, and then we count the results. So very much the same as we had with the RxJava version. We just use the various types for Reactor as opposed to RxJava, but otherwise it's pretty much the same thing. And so this particular count matches function can then be used in our stream down here. And I did this on purpose because I found it made things a little bit less verbose. So let's take a look and see how it works. So basically what we're going to do here is we're going to use the flat map method here. So this is kind of like the then apply method in a way in completable futures. So when the mono is ready, we go ahead and then do the code here. So we're going to go ahead and convert the root folder dirent into a flux, so a stream of entries. We're going to then call flat map, and this uses that flat map idiom to do all this stuff either concurrently or sequentially, depending on whether we've configured it one way or the other. And we pass in the count matches function. So you can see that rather than repeating this code down here, which makes this particular flux stream way too long, we kind of absorb it up a bit and move it into a standalone function. Of course, I could move it into a method and call the method reference there. So I'm, just experimenting with different approaches. I kind of like this approach because it really belongs there. It's really part of that implementation. If I was going to reuse it and other methods were going to use the same code, I would be more tempted to extract it into its own method, because then I could pass it in as a method reference in multiple places. If it's just something that's within the scope of one method, as it is here, I'm keeping it kind of hidden as a function object as opposed to a method. Okay, so what I end up having here, as you can see, I have a flux of longs. So all the stuff here will then go on in parallel, and I'll end up with a flux of longs. And then I'm going to use the reduce method. And reduce is very much like reduce in Java streams. So you say reduce, you give the accumulator, which is going to go ahead and do the reduction, which in this case will sum everything up. And what reduce returns is it returns a mono long. So in this particular case, there's one element that's done because we've reduced it all into one element. And then if the stream was empty, then we return 0. Otherwise, we return whatever the reduced to. And then the last thing we do on the way out here is we go ahead and we'll use the do on success method, which is again kind of like then apply in completable futures, and we get the number of word matches and we print those out. And then we also block until we're done. In a production application, of course, I wouldn't have to call block if I arranged things so that I wouldn't run off the end of main before the computation was done. So that's another approach. And you can see this looks very, very much like the RxJava version, just a little bit more Java 80-ish in some ways. And the last implementation we're going to look at here is count lines. And count lines has got yet a different style. In this approach, I define a pair of helper functions, which are function objects. One is called count one durant lines, and the other is called count all durant lines. And you might guess that count all durant lines is going to use the count one durant lines function in its implementation. And what we end up with here then is a very short little stream that's doing the actual processing. So when the durant root folder has finished initialization, we then go ahead and call flat map, passing in the count all durant lines function object, and then that goes ahead and runs, and we'll see what it does in a second. And then when we're all done, we go ahead and basically call do on success, which gets the line count, which we then print. So this is just a little bit more factored, so it's perhaps easier to read depending on your point of view. Some people like really long streams. I find that gets unwieldy, so I like to chunk them up into smaller functions in this case. So you can see here, count one durant line, lines takes a durant. We convert that into essentially a flux of these things using the just concurrent if helper method in Reactor utils. We get rid of everything that's not a document, and then we take each document and we split it up using split as flux into a flux that's demarcated by new lines. So it's a flux of strings that are split by new lines. And then we count the number of new lines in that particular document. So that's what count one durant lines does. That's that function. And then down here we have count all durant lines, which takes the root folder, not a given durant that's part of the root folder. And then we go ahead and convert that into an iterable using flux from iterable, which is a helper method that makes it iterable. And then we use the flat map idiom to count the number of lines in the folder, either sequentially or concurrently, again, depending on how we've set the factory up here for just concurrent if. And so this will end up giving us a flux of longs, which represents the counts of the durants for all the different directories and documents we've been looking at that level. And then once again, we use the reduce method, which is kind of a terminal operation in a sense, which reduces to a mono with a single long, and then we return either 0 or whatever that summed to. So you can see 3 different styles of programming using Reactor or RxJava-like approaches. One really refactors quite a bit so that the actual code is very concise. Another one sort of does it partially with factoring out some of the functions, and the other one just says, the heck with it, everything's going to be in line. So you can kind of pick your alternative that you like best. Let me now go over and take a look at another one of the tests. This is the parallel tests. So in addition to the ones that either run concurrently or sequentially, depending on the flag we pass in, we have another set of tests that always run in parallel, and they just hard code themselves to use parallel fluxes, which is fine. The parallel flux syntax doesn't lend itself as conveniently to toggling back and forth between concurrent and sequential the way that the other fluxes do. So fluxes can be toggled, but parallel fluxes are parallel, and the syntax is slightly different, as we'll see. So here is create folder parallel. We already looked at create folder parallel. It uses the same trick as before. We go ahead and do this in parallel, and then we cache the results. So we don't have to make this a hot mono. There is no such thing really as a hot mono. There's a hot flux, but it just got awkward, and cache seemed to work just as well. So here's count lines parallel. Count lines parallel is partially refactored. Now, because of the way that parallel fluxes work, we don't have to do as much refactoring into intermediate helper functions because it's more concise. But we do have one helper function called count lines, and count lines is going to split the document up according to new lines and then count the number of new lines. And you'll see here that we're going to use that in our parallel flux implementation. So here's the parallel flux implementation to count the number of lines. We use flat map. When the root folder mono has completed, that gets us a completed root folder. We then convert that into a parallel flux, and we use a little helper method I wrote called from iterable parallel. And this takes an iterable and it creates a flux out of that iterable. Then it creates a parallel flux, and then it schedules that parallel flux to run on a given executor, which in this case is the common fork join pool. So now we have a parallel flux of durance. We then go ahead and filter out everything except documents. And then here's where it's a little bit more concise than the version that uses fluxes. So parallel flux version can use flat map to count the number of lines. So it's going to count the number of lines in the document. And it does this in parallel with other documents. So other documents in the durant. So basically what it's doing is it's going through this and it's winnowing out everything except documents, and then it's counting them all in parallel. And that's because we're using a parallel flux and the flat map from parallel flux. We then go ahead and reduce the results into a single result, which either will be non-empty or empty, in which case we turn it into 0 if it's empty. And then we do the same trick of do on success. So you can see that this approach is just a little bit more concise than the other approach that uses regular fluxes. And that's because parallel fluxes are optimized for parallel processing. And search folders parallel, really pretty much the same thing. We use the same technique, except this time we're going to do occurrences counts as opposed to counting the number of new lines. We're going to count the number of occurrences, but same basic idea. We convert the root folder into a parallel flux stream of durance. We only look at documents. We count the number of matches using our little function up here. We reduce, default is empty, and do on success. So you're probably starting to see a lot of commonality showing up in these examples, and that's a good thing. Commonality is good. It means that we've kind of found some useful patterns that make it easy to process, and there should be few surprises. So those are the main things that I wanted to show you. But before I answer questions, let me run these things and let's see what the performance is. It's really kind of interesting to see what the performance is of the Reactor framework, and especially the different versions. So the first thing to note is that everything produces the right results. So we get the right number of completable future matches, we get the right number of lines, we get the right number of entries. So whether we do this processing concurrently, sequentially, or in parallel, or parallelly, it always gives the same result, which is comforting. Now let's take a look at the performance of these different approaches. So as you might expect, the sequential versions are going to take a lot longer because there's just one thread as opposed to basically 8 threads in our pool. So search folders sequentially takes a long time. Count lines sequentially takes a fairly long time. Let's go ahead and run this again. It's funny, sometimes you get different results if you run it multiple times, just the non-determinism of parallelism. So you can see here we get about the same results. So let's see. Yeah, this is pretty interesting. So search folders sequentially gives us this amount. Search folders concurrently gives us this amount. This concurrent version is the version that's using the Reactor and RxJava flat map idiom for concurrency. But then if we go ahead and take a look at search folders using the parallel flux version, it's substantially faster. So it's about 3 times faster than the sequential search folders and about twice as fast as the concurrent search folders. So that leads me to believe at least that the parallel flux implementation has been nicely optimized in the Reactor framework. Again, just for kicks, just looking at these differences. This time it's even more dramatic. So this time when I ran it, you can see that sequential execution was here, and it's about 4 times faster now to do the parallel version. And this time, the parallel version is a little slower. So your results vary a little bit, but in general, the ones that are running concurrently or in parallel are likely to produce much better results. A couple other things that are worth noting: the count entries is just super fast no matter what, and that's because it's really just doing a count, so it doesn't have to do a lot of things. In fact, the concurrent counting is actually slower than sequential counting because there's more mechanism required to set things up to run concurrently. So the count mechanism is obviously very fast here. It's just looking at the results, looking at the sizes. Creating a folder sequentially takes about 270 so milliseconds in this run, but creating a folder concurrently takes no time at all, it appears. And that, of course, is the usual thing where the concurrent version returns almost immediately, and it doesn't actually count anything towards the time taken to do the concurrent processing. That's done elsewhere. You'll notice that the create folder parallel version is a little bit slower. I think there's a slower mechanism in setting up the parallel fluxes, but they're both very, very fast. Whereas creating the folder sequentially is obviously a lot slower because it had to actually sit there and chunk through most of the recursive folder structure on the file system in order to get access to the elements it needed. Let's see, count lines. You can see that count lines in parallel is a little faster than count lines concurrently, and they're both substantially faster than count lines sequentially. So it's obvious you always have to be careful overgeneralizing from a few results and a few tests. But if we ran these tests consistently, I think you typically find that the sequential ones are way slower than either the parallel or the concurrent ones. And if you look at the actual code required, the coding effort for the parallel approach is actually a little more concise than the sequential or the concurrent approach. But the sequential and concurrent approach have the benefit that you can toggle concurrency on and off. So it's much like the benefit of using parallel streams or sequential streams, where it's really easy to write something in a sequential stream, debug it, get it working, and then turn on parallel streams, and boom, you typically get a big speed up without much extra complexity in programming. Okay, so that's really what I wanted to show you today. I think this is really instructive. I've had a lot of fun learning the Reactor framework. It's really quite simple to understand. And once you understand RxJava, the transition from RxJava to Project Reactor is very simple. It's much the same set of patterns. Like I said before, I personally think that the Reactor is a cleaner overall design. The one downside with the Reactor stuff is it really isn't very well documented. There's far fewer examples of Reactor. But the good news is once you understand RxJava, which is much better documented, it's pretty easy to learn how the Project Reactor stuff works. It's very much the same. And in many ways, it's cleaner because they use the modern Java features more consistently. Okay, so with that, let's go ahead and let's go back over here. And I will take some questions. Let's see. I'm never quite sure why. Come on. There we go. That looks better. Zoom is always trying to flummox me in some way or another. Okay, let's see. So question number 1. Why do we have to call sequential at 1, 2, 3 if we're calling collect on the next line? The reason why that's the case, and let me go back and show what you're referring to so that people are not befuddled as to what you're asking about. If we take a look over here and we go back over to the parallel version of this stuff, let's see if we can find test parallel version. Oh, I know where we were. Let's see. We need to go over to folder, I think. Folder. And it should be up here. Yeah. Okay. So what we're doing here is we've been processing using the parallel flux. But one thing to note, parallel flux, much like parallel flowable, has a subset of all the mechanisms that you would find, a subset of operations you would find with either a regular flux or, say, a flowable or an observable. So what you need to do if you want to use things like collectors, we have to go ahead and essentially turn it back into a sequential mechanism. It's basically like doing a join in a fork join model. And so now we're going to end up basically converging the parallel fluxes and all their content into a single flux, and then we can collect the results. So think about it as just the joining of a bunch of parallel computations. So it's like a collector would form in a parallel stream. It's a point of entry. And you need to do the sequential in order to get us back to the point where we can do these joining mechanisms. There's other things that you find with fluxes that you just don't find with a parallel flux. So this is an example of those kinds of things. Let's see. Let's go back and stop sharing. Okay. Whoops. What happened to my chat? There's my chat. Okay. Flat map in Java 8. In Java 8 takes an input and returns a collection of output elements. I wouldn't say it returns a collection. They're always returning streams. So in Java streams, flat map takes in an input stream, and then it returns an output stream that could have the same number, less than, or greater than the number of elements in the input stream. So you're always returning a stream in both cases. With flat map in Reactor or RxJava, it's much the same thing. You're taking in a stream, and then you're typically doing stuff that denests the stream. So it really behaves almost identically in both examples. So it's not that you're getting one output, it's that you're getting a flux as output. And we do this to avoid the nesting problem that you would otherwise get. So you're getting one output, but that output is a flux, which is basically a stream. And the same thing holds true in RxJava as well. How can functional operators be debugged during execution? So there's a bunch of cool mechanisms that they have to help you in Project Reactor. And in fact, let me go over and find something for you. I found a really great article the other day that I should be able to find here. RxJava versus Reactor. See if I can find it. There we go. Okay, so let me share my screen and we'll talk about this. So there's a bunch of debugging techniques you can use with all these mechanisms that you should get very used to if you don't want to drive yourself insane. So here is the article I'm talking about. This is by Thomas Nukowitz talking about RxJava versus Reactor. So if you Google Reactor versus RxJava, TOMAS, T-O-M-A-S-Z, you'll find this article. And he compares and contrasts both these frameworks against the set of criteria. And one of the criteria is debugging. And in the debugging discussion, he talks about how you can turn on this thing called operator debugging. So this is one answer to your question. So one thing to do is turn on this feature, and then he shows how it makes it a lot easier to tell what's going on in the logs of what's happening. And then the other thing that you should do is get used to using the log operators. The log operator that will print what's actually going on under the hood of the framework, so you can see what it's doing. So that's extremely useful. He also has some other interesting discussions in here, comparing and contrasting the type systems of RxJava versus Reactor, and that could be interesting to look at. His conclusions, I think, are pretty close to what I would say at this point. So if you're using Android, you're most likely going to be using RxJava. RxJava is very well integrated with Android using RxAndroid, and it goes back to older versions of Android, versions before Java 8 was integrated. If you're using modern versions of Android, I think it's maybe Android O or later, you can use Project Reactor there as well, because they supported the Java 8 features at a certain point in Android. There's also this whole issue of documentation and performance, and so he basically says at the moment it's kind of a tie. Each one has pros and cons. but the kind of the velocity, the derivative is heading towards Project Reactor because it's more modern, it appears faster, and I honestly think it's just cleaner. It's always easy if you start from scratch, and do things in a more modern way, and they did a very nice job. So your mileage may vary. I think it's easy to move back and forth between the two. But to answer the specific question here, in my experience, if you use the debugging mechanisms he's talking about in conjunction with log, that can be a big help. So another comment, which I completely agree with, the Reactor framework is really kind of the best of all worlds in a sense. In fact, one of the really cool things about the Reactor framework is you can convert monos and fluxes into completable futures and into streams quite easily. And let's see if I can show how that works. That's really cool. I was playing around with that the other night, and so you'll see in some of the places in my test programs, like over here, for example. Let's go find a test program. So you'll see in this particular case, I ended up going ahead and doing this do on success thing and so on, and I got back the results. But I could also have done some other tricks. Let's see if I can find one that's easy to explain. What you basically can do is if you have a mono, you can say to the mono, .toFuture, turn it into a completable future, and then do completable future operations on it. And if you've got a flux, you can take the flux and you can say toStream, and you can convert that into a Java 8 stream, and then you can do stream operations on that. So those are some nice ways of being able to, kind of mix and match the two worlds. And also, as I showed here in a couple of places, the ability to be able to use things like Java collectors to terminate the flows. That's a really cool capability as well. In the next couple of days, we'll look at some other advanced features of Reactor, like they have this thing called collect list, which is very cool. They also have some things that you're probably familiar with if you're familiar with RxJava, like zip with, and this other thing called, I think it's called first. So if you have two different monos, you can pick whichever one emits first and choose that. So that's very much like completable futures, either, I forget what it's called, but there's an either method where you can take either one, whichever one finishes first. So we're going to look at some other advanced approaches in the next couple of days, because I had a lot of fun this weekend doing a lot of programming with the Project Reactor stuff, just to figure out how it all works. Let's see. So the observation here is that collect is not the same as collect in parallel streams. There is also a collect that's available in the, I believe there's a collect that's available in a parallel flux. I'd have to go and look at that. In fact, what the heck, let's go ahead and take a look and see what we can find here. Share this, and let's go type in Reactor parallel flux. And we go over here, and let's see. So yeah, there is a collect in parallel flux, and you can see that the collect in parallel flux takes a supplier and a buy consumer, and it collects things up, and it's a little bit wacky, and that's why I didn't use it, because I found it a little wacky. But there are other mechanisms you could use to kind of group things together in much the same way. But the good news is the sequential stuff is just an easy way to sort of syntactically turn the parallel flux into a flux, and then you can go ahead and use collect on it. So it's pretty easy. So another question, what are the kind of problems that reactive streams are trying to solve? Well, that's a good question. So let's take a look at, let's see, reactive programming, pitfalls. So there was a nice tutorial. Let's see if I can find this. Yeah, here we go. So again, this guy, Tomas Nukowitz, has a really nice tutorial about lessons learned from reactive programming. And if you watch the tutorial, probably in the first 5 to 10 minutes, it's only about, looks like about 40 minutes long. the first 5 to 10 minutes, he shows a real cool diagram. Let's see if he shows it, if I can find it. Maybe I can't find it, but let's see. He talks about, yeah, here's the example. I guess it's actually not first 5 to 10 minutes, and it's within the first 20 minutes. His basic point here is the following. If you have programs, if you have application requirements where scalability is really important. So remember, RxJava came from Netflix originally, and they were really concerned with scalability and being able to write kind of common code base that could work across all the different devices that they had. So, and they had a huge scalability challenge. So scalability is really driving what you're trying to do. And let's see if I can increase the size of this thing. Doesn't get too much better. I can't read it. That's the problem. Oh, there we go. Okay, so if you look at this chart, it's basically software development time, hardware, and maintenance. So his basic point is, if you really care a lot about performance and scalability, then a reactive approach is for you. But it doesn't come for free. And the thing you get charged for is the complexity of developing it and maintaining it. So that's the tricky part. And why is that tricky? Because a lot of people today haven't really got their heads around the concept of reactive programming, even though it's very popular. And they also haven't got their heads around reactive programming at scale. So the point here is that it's not a tool to be used for everything, but for people who have a real need to use their hardware resources effectively, and people who just like to play around with cool new stuff like me, that's kind of the market that should be considering this technology. So I recommend you watch his tutorial, because he basically says, there's no such thing as a free lunch, and this stuff is cool, but it's not perfect, and it does come with some additional complexity. So the reactive design pattern is a pattern I wrote a long, long time ago, back in the mid-90s. And in fact, that pattern is all about making your programs reactive. They can respond to changes in their environment, and then they trigger callbacks, so you don't block. So there are certainly aspects of reactive programming that have that flavor, for sure. Let's see. Is it true that reactive programming is going to be an absolute need? Nothing is an absolute need. There's still people out there programming in COBOL. In fact, you guys probably saw a couple weeks ago, there was a big problem in New Jersey, because they needed to find, in the US state, New Jersey, because they needed to find COBOL programmers to maintain their old legacy systems. So nothing is ever a necessity. There's all kinds of other factors that make things relevant and make them profitable and make them compelling. So there's no single thing that is going to take over the world. I will say, however, if you take a look at the evolution of most programming languages over the past half decade or so, they're all madly rushing to add functional features to them if they didn't start out with functional features to begin with. So if you take a look at, obviously, C#'s been doing that, C++ has been doing that, JavaScript's been doing that. I think it's kind of always been that way. Java, for sure, has been doing that. So all the major languages, and I'm sure I've missed somebody's favorite language, in which case I apologize, but all the major languages are adding these new features. And I think that once you get your head around functional programming, it can be very easy to write convenient code. Having said that, you still have to have a good design aesthetic, and that's not always easy to get. So for my money, the combination of object-oriented design from a structure and architecture point of view is very beneficial, then combined with the functional programming features to handle the computationally intense parts of the code. And why this is so cool is because it makes it absolutely trivial, usually, to switch between sequential and concurrent or parallel code. And that's something that was always extremely difficult to do in earlier paradigms, particularly object-oriented paradigm. So it was very hard to go from sequential to concurrent or parallel with object-oriented programming. You had to do a lot of rework. You had to make an intentional choice up front to go one way or the other. Whereas with a lot of the reactor models, the reactive models and the functional models, it's real trivial to make changes to go from sequential to concurrent and parallel. Okay, so at this point, I think I'll just point out what we're going to be covering next. So let's go to my GitHub repository. I've got a bunch of other cool new RxJava related things that we'll probably go over in the next few days. So I've gone back and I have re-implemented my RxJava EX2 example. So now we can compare and contrast very, very cleanly the RxJava code with the Reactor code with the Streams code. So that's kind of fun. It's real easy. It's basically apples to apples comparisons. And when all is said and done, they all kind of look about the same, which is good. It means that these paradigms, when done properly, can converge and be very familiar to people as they move back and forth between them. Another thing that we're probably going to take a look at, I've started a new Reactor folder, and I've got a new example in here called EX1, not a very interesting name. I'll put a little legend in to make it more clear what it does. But this basically shows a bunch of really cool features showing how to reduce and multiply big fractions using a bunch of stuff in the Reactor framework. And so we'll probably go over that. We might go over that tomorrow. I've got a completable futures version of this code as well. And it's really interesting to compare and contrast them. And every time I work on this, I try to come up with cooler, newer ways to make it work. But I've got a really interesting test harness that shows off all this stuff. And it also demonstrates how you can have a lot of asynchronous code all running in the background and then wait for it to happen and wait for it to finish. So if you have time to look at this stuff before we do things tomorrow, feel free to take a look and come and ask some questions. But otherwise, as always, I always appreciate everybody showing up. Oh, wait, there's one more questions. Various APIs you used, are they going to be good enough to write some applications? I'm not quite sure what you mean by that. If the question you're asking is all these little helper classes that I write, like Reactor utils or the RxJava utils, those are very useful. If I was writing production RxJava or Reactor code, I would absolutely use those little helper components because it's so repetitive to write all this stuff by hand. It just gets to be a blur of boring repetition, which is never good. Whenever you start repeating yourself, it's always a bad thing. So this code is very helpful. If you're asking, can you use Reactor or RxJava to write production code? Of course you can use RxJava and Reactor to write production code. So I'm not really quite sure what you mean, but if you clarify it, I'd be happy to take a thought into that. But I think if you're just asking these little helper methods, yeah, sure, they're really useful, and I would use them anytime I could. Okay, well, again, thank you guys so much for coming, and I will hopefully see you soon.